All right. Now, you want to start with your question first, or do you want me to start teaching? And Mike, answer. Which picture are you looking at?
Well, I was looking at figure 20.2, and I was wondering,
Wait a minute. 20.2. I got to find it. There it is.
why is the temperature negative 56 at 20 kilometers, but only 25 at 40 kilometers?
Even though I took a class in meteorology about over 40 years ago. And I do remember them talking about then. I even have a book. I still have a book that would teach that to me. But since I've never had to do that, I don't know the exact answer. I know that the phenomena they figured out very early when they put weather balloons up, they thought it would just get colder, 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 colder. And they noticed there was a zone where it actually got warmer. And I'd have to read. Actually, right now, I don't know. Right now, on top of my head, I don't know the answer why there's a warm zone there. I would have to look that up. That's a great question, though. Yes?
Look it up for extra credit.
Yeah, and again, if you look something up, you always highlight what you think is important about it like that. And your question is, why is there a warm zone? Is it sandwiched between two cold zones? Yeah, that'd be interesting.
Well, it's not only cold zone because it's like it's continually increasing from 20 kilometers to 40 kilometers. It's still getting warmer.
Yeah. Which is, I think, interesting because temperature is different than heat. And temperature has to do with the movement of particles, the average kinetic energy of the particles. Well, you have a whole lot less particles up there. And so that's interesting about looking at the definition of temperature. If you have very few particles, what happens if you have a thermometer there? How many particles are hitting the thermometer anyway? That's a great question. Yes?
So this is a little off topic, but I got 2 extra credit projects that we talked about. Right here, do you want me to bring them up for the class or just give them to you after?
Do I know what they are?
Yeah, so we talked about this one in class. We were talking about the freezing and melting point of brake fluid, and then you and I had a conversation after. So I did some research on that, and then I have the little ice melting water.
Oh, the ice melting thing, you can just make sure names on it, hand that to me, because I've gotten 3 of those already. I would like, if you want to tell everybody what you found out about brake fluid and all that, I'd like to hear that.
All right, so from what I found out was there were 3 different types of brake fluid, and they were all based around some solution called glycol ether. And so the first one.
Glycol ether?
Yeah.
Okay. It looks like ether. Wait, I want to hear this.
So the first one, they all have the same freezing point. They all freeze at negative 40 degrees Celsius, but they vary a little bit in boiling point. So the 3 types are dot 3, dot 4, and dot 5. So the boiling point for dot 3 is 204 degrees Celsius, and freezing is negative 40 degrees Celsius. Then dot 4 is 232 degrees Celsius is the boiling point, same freezing point.
What's the difference between the boiling points, only 8 degrees?
That one is 28 degrees.
Oh, 28? Okay.
And then the third one is dot 5, and it is 260 degrees Celsius. And from what I read, they can't use dot 5 because it has an issue with like getting diluted with water. I couldn't totally understand it, so that it wasn't as reliable in all situations as other ones were.
That's interesting that they would have a hydraulic fluid that would allow water to get into it.
Yeah, I didn't totally understand
Yeah.
how it worked. And then
But, okay, go ahead.
the aviation, the stuff they use in planes is called phosphate ester. I don't pronounce it.
Okay.
right. And I could not find an exact boiling point for it, but the freezing point was negative 53 degrees.
Oh, so it's even colder.
It's even lower.
Interesting. All right, I had all that stuff you said. I've never heard those numbers, so that was great. You can go ahead and bring that up here. I love that kind of stuff where you, I think this book tends to lend itself to go looking up stuff also if you like that kind of stuff. And I'll take the other one too if you want to bring that. Anyway, so aviation fluid, minus 53 degrees Celsius, even colder than minus 40. So I guess maybe there are some planes that actually go pretty high up there. Whoops. Okay, is this easy to see?
No, but I couldn't find it colored.
Okay. What I mean, is it marked? Like you can see the lines?
Oh yeah, I put a rubber band around where the water level is.
Oh, okay. Are these in order? Do I have like order like 1, 2, 3, 4?
I can put them in order.
Can you do me one favor? Just right on there, what I'm looking at, is this the water level with no ice?
Yeah.
Put water level, no ice, and then water level with ice, water level, melted ice, so I can tell which one's which, all right? All right, well, let's get going here. I want to start with when we were talking about a barometer, and the barometer, without a doubt, is one of the number one instruments they're going to use in meteorology. And I'm going to give you a quick weather lesson today, very quick. So if you happen to go home tonight and you watch the weather forecast, you'll understand it a little bit more, okay? I'm not trying to tell you we're going to do 2 years of meteorology school. I want to give you a 15-minute lesson so you can look at a map and say, oh, I sort of know why that's happening now. You get it? So you just appreciate the weather forecast just a little bit more. All right, so here's a barometer. And one thing about this chapter that I thought some people were weak on a little bit last year was why is this working? Like, why does a barometer even work? If I have a really long tube and I fill it with mercury and I put my thumb on it and then turn it upside down and put it in a bowl of mercury, why would I want to take my thumb off? Wouldn't that really dense mercury just come all the way out and spill over the floor? You would think so. As a matter of fact, when I take my thumb off, it does come out. It comes out and it does start filling up the bowl. But then something amazing happens. It stops. It stops coming out of the bowl of the tube, and it stops right there. It's like, and if I'm at sea level, what is the height of this column of mercury, which we call normal atmospheric pressure? What's the height of it? How tall of a column of mercury is going to be standing there? What's that number?
76 centimeters.
And that's the same as 760 millimeters, right? Which is the same as 760 torr. Again, there's so many different pressure units, aren't there? Which is about 101 kilopascals, something like that. Now, why is this happening? Now, here we go. Be careful. Which one's greater? The weight. Oops. Sorry. Sorry. Thank you. Which one's greater? The weight of the mercury pressing down on this amount of area, the force per area, that's pressure. Which one's greater, the weight of this column of mercury or the weight of a similar diameter tube of air that goes all the way up to the top of the sky, 30 kilometers high? Which one has the greater weight? What do you think? All right, let's answer one more. Go ahead. They're equal. And so think about this. There's no reason why this mercury shouldn't come out unless something's pushing on this other mercury. If I did this same experiment in a vacuum, let's say I had a robot, and because I'd be dead, but if he's in a vacuum and the robot took his thumb off, all that mercury would come out. It would come out and come out and come out. There'd be nothing pushing on here, nothing to prevent it from coming out. But the air, the weight of the air is actually pushing here, isn't it? Now, it just so happens, though, that this is a really dense material. Could you make a barometer out of water? Could you do the same thing with water? Really, a tube of water, turn your thumb upside down, a bowl of water. Could you make a barometer out of water? Yeah, you're going to answer it. Good.
You could, except it'd be very tall.
It would. How much taller?
10.3 meters.
And you know what that is? Mercury is 13.5 times more dense than water. I bet the mercury barometer is about 13.5 times smaller than the water. So if you take 13.5 times 76 centimeters, you're going to get something around 10.3 meters. What if I made a barometer out of rubbing alcohol whose density is 0.8? What do you think? Any estimates? Let's make a barometer out of rubbing alcohol whose density is 0.8. Would it be taller than this? Would it be taller than 10.3 meters? Yes, that's good thinking. That is good thinking, all right? Because it was less dense, it doesn't weigh as much, does it? And so that column would be even higher, wouldn't it? And what if I made a barometer out of air? How tall of a column of air could be held up by air? 30 kilometers tall. What if I made a barometer that was mercury, this diameter, this area, and in my another one, a really big mercury barometer. Wow, like 3 times the cross-sectional area. How tall of a column of mercury would that be?
76 centimeters.
You're right. And if you're thinking like that, and you said, you know what? Each square centimeter can hold up 76 centimeters. Well, if you got 5 of them, then all of those will be held up 76 centimeters, won't they? Yes?
Would a barometer work the exact same in a room like this where the air is piled 10 feet high?
What's interesting is, even though we're in a room, the air pressure in here is almost identical to here. The only time it would be different is when the blowers come on. If the blowers come on for about a second and a half, there'll be a little more pressure in this room, and then eventually it'll work its way out and equalize like that. So if I had a barometer here and I really measured small differences, every time the blowers went on, I'd say a little higher pressure, then it would go back. Good question.
Why will the air pressure be the same in here as outside?
If this was completely sealed to the outside, and then you let the blowers come on, then it would just keep building up. Now, if the walls can't expand, then the pressure would have to get bigger and bigger and bigger. But right now, we have lots of openings. There's openings around that door, and it can get out. We can't keep the air. The air can get in and out of this room right now. Yes?
So with as you go up in higher altitude, you can't breathe. Is the reason because the air is thinner, so there's not as much oxygen, or because the oxygen sinks because it is more dense than the air, or both?
Okay. As far as having trouble, if you've ever been up in the mountains and you start climbing up and you say, why am I out of breath so quickly? Each breath you take would have less air in it, and air is nitrogen and oxygen. So if you have less air, you have less oxygen in every breath. If I gave you a tank of oxygen, you wouldn't have any trouble going up that mountain. So it's not because anything's more dense, it's just that air is less dense, and so you get less air per breath. Now, they actually do something, I think I mentioned this to you before. Some people before the Olympics, they will actually train in places like Colorado, like Denver, Colorado, or they'll go to places that are like a mile above sea level. And at first, they'll have trouble training, they'll get out of breath. And if they stay there for a certain amount, I forget, it's 3 months or something like that, if they train for 3 months there, the human body, God's amazing, the human body will sense that they're having trouble getting oxygen and will start making more red blood cells than normal. Red blood cells die by the millions every day, and they get made by the millions. But you'll start making more and more red blood cells per day than you used to. And then you'll start acclimating. You'll say, I feel okay. I feel okay there. But then when you go back and the Olympics are down at sea level, then you'll actually perform a little bit better because you'll have more red blood cells there, and that effect lasts for at least a month. And so that's kind of interesting too, is I have more red blood cells, I can actually deliver more oxygen per second than I normally could. So some real Olympic trainers actually do that on purpose. All right, well, does everybody understand the barometer then pretty well? I want to show you, I passed it around last period, but I'm not sure where it ended up. Here it is. Yes?
So, like, if your body started making more red blood cells, like, if you're a mile above sea level, like, if you were in a place like Death Valley, where it's like you're lower than sea
Wow.
level, would
Okay.
it make more
You know what?
less?
Even though I've never read that, I'd have to say yes. But I wonder if there's even, you actually have more air pressure when you're below sea level. How about people who work in the mines? Let's say they work a quarter of a mile down in a mine, and they work there every day. Would they develop less red blood cells per day? I've never read that. But I do know they have more pressure, so that means maybe every breath, would they have a little bit more oxygen every breath? If you can find anything like that, I see why an athlete would want to do that, but what would be the purpose of trying to make less red blood cells? But it would be interesting. I've never read it, ever. All right, so what's this right here? even though, I don't think I ever had one, I don't think my parents did, my grandparents did, I remember that. So maybe your grandparents, anybody seen these before, ever? They usually put it on a piece of wood, you hang it on the wall, anyway, what is this? It's a barometer, but it's not a mercury barometer, what is it? It was in your book. What kind of barometer is this? Aneroid. And what does aneroid mean? Anybody? No liquid, right? No liquid. So this is a barometer. And what they did is this little box here, it looks like a piece of copper. It's actually a hollow piece of copper, and they've taken a certain amount of air out of it. So it's kind of like a partial vacuum in there. And so let's say that a high pressure system comes across Greensboro, it would actually squeeze the outside of that can into a little smaller space, and that would make the dial go up, high pressure. But if a low pressure came here, it would allow the sides of this little can to expand, and that would make the dial go to a lower number here. So I want to give you about a 15-minute lesson on meteorology, okay? Maybe 10. And this right here is the kind of barometer you might see in somebody's house. I doubt whether you're going to see a mercury barometer. I will say that in your area, in my area now, almost everything is digital. And so you're not going to see this or a mercury barometer. You're going to see a digital version of a barometer, and it has something to do with pressure changing, and change that to a little electrical signal, and it shows up as a number on a screen. So I think that's what you're going to do. I want to mention, before I do my weather lesson, I want to show you, I don't know if you know Jonah Chu. Besides making good Rice Krispie treats, Jonah plays piano, and he plays saxophone. He also is interested in everything. And but anyway, he wants to be a pilot, and he actually got his pilot's license when he was young. And last year he was in this class, and when we talked about that, he kind of got interested in it. And I have this saying, we're going to use LabQuest later, but I have a LabQuest, a little portable computer, and I have a barometer. I have a digital barometer that hooks up to it, and you can get the barometric pressure anytime you want. Anyway, and I showed him how to use it if he wanted to have it set where it takes a reading like once every minute or once every 5 minutes or whatever. You can set it whatever you want. And he wanted to take it with him, and yes, it was $300 and $400 worth of stuff, and I had to trust him, but he took it with him on the weekend, and little did I know, he took it with him on the plane. And little did I know that it was his first solo flight. Now, I don't know if you understand what that means. This other person's been with you, and if anything goes wrong, they'll take over controls, all right? The first time he was going to fly a plane by himself, he thought I'd be really nervous. But he also thought, I'm going to do a science experiment at the same time. And so he said it, and I actually have that, and I'll try to find it. It's in one of my files. But we came back, and we printed it, and you can actually tell as he went up, the pressure got less and less and less. And you can actually look at his flight. And he actually did some other maneuvers in there, and you can actually see the pressure go up and down, up and down. And I thought that was pretty neat. Yes,
So how does the cabin of a plane work? Does it just add more oxygen to the air?
Okay, now, jetliners that fly really high, they have to be different than just a single-engine plane. A single-engine plane, they're not going to go very high, so they're going to be open to the air. They're going to have probably the same air pressure in and out. If I had a private jet, it would be pressurized because they probably fly really high. So regular planes, same pressure as outdoors, and other ones, they actually take air with them, and then they pressurize the cabin. Now, sometimes they pressurize it too late. You ever done that? You ever flying a plane, and you can feel your ears, and then eventually, they keep putting more and more pressure in there, and then you feel kind of normal. So that's what they do there. They take extra, they pressurize the cabin. And the good news is the plane can handle that pressure and not blow apart. That's good. And so it actually pushes back on you. All right, well, anyway, let's do a quick weather lesson, all right? All right, so we know that, and this is a very, very short lesson, okay? But I just want you to be able to look at a weather forecaster and say, I know a little bit more about what you're talking about. Well, air gets moved around a lot, and because of different heating zones, and you get air moving, it piles air up, and it makes troughs of air and mountains of air. Well, what happens is on a map, what you'll see is something like this. So here's a terrible drawing of the United States, and there we go. But what we're going to see is you might see something like this, an H, okay? And then you might see somewhere else an L or something like that. And you say, well, what in the heck are the H's and L's? And those are highs and lows. So even though that's what it looks like by looking down at it, what would it look as cross-section? A high would be kind of a piled up part of air. It's like where air is piled up. And I think about that. What happens to my barometer if a mountain of air, normal amount of air sitting on top of my barometer, and then the high comes over Greensboro? You're going to have more weight of air pushing on that. And what's it going to do to this column of mercury? It's going to push it up. And they say the mercury is rising. All right, that's a high. So one of the characteristics of a high pressure system is it is a mountain of air, a piled up air of air. It does cause a barometer reading to rise. And okay, and next, air that is a mountain tends to want to flatten itself. And it should flatten itself in every direction. But because the Earth's rotating, we actually don't get the air falling equally, and so it starts to move. And in the northern hemisphere, a high-pressure system, the air will sink and rotate what we call clockwise. So the air on a high will go like that. Now, what happens to clouds and things if the air is falling and leveling itself out? It evaporates the clouds. And so a high-pressure system, usually you don't have any clouds. It's very sunny. It could be in the summertime and sunny and hot. It could be in the wintertime, sunny and cold. But it's sunny. And it actually evaporates clouds. And those are the characteristics of a high-pressure system. Now, I told you this yesterday. If we had a city like Greensboro here, and somebody said the high pressure is tracking due east, what would happen is the first thing that would hit you on that high pressure system would be winds coming from about like this direction here. And winds are named from the direction they come from. So that the meteorologist might say, expect the winds to come from what? The north what? Northwest, okay? So the winds will come from the northwest. And how do they know the speeds of the winds? And that's interesting too. This right here, some mountains, some highs, are kind of like big and not so tall. And so if the pressure difference is very small between the highest part of the mountain and the small and the lowest, then you're not going to get very good winds. But what if the high is really high and the outside of the high is kind of low? Expect a lot of wind, and they can actually predict what speed the wind's going to come at, what direction, and what speed. So next time you hear them, they say, well, winds are going to be like over 30 to 40 miles per hour. How do you know? How would you possibly know that? And they know that because of the pressure difference. Now, what if this high then keeps going, and now it's over here? Now the high has moved east, and now what would the winds, what would happen there? The winds may have started from the northwest, but later, a couple hours later maybe, they'd be what kind of winds? Northeast. See that? And so if they say the winds, expect the winds to shift from northwest to northeast, they might do that. What I like is, I think it's kind of interesting, is what if, this is Greensboro right here, what if a high is moving like this, and we had normal, nice temperatures, okay, and this high is coming, highs go in a clockwise direction. Well, guess what it's going to do? It's going to pull cold air from Canada. It's going to pull that air with it. As it goes like this, clockwise, I'll do it this way. As it goes clockwise, it's going to pull air down from up here. And that's why the temperature might change, because all of a sudden, wow, where'd it get all that cold air? It was being pulled down by that high pressure. Sometimes you'll have a low, in the summertime especially, and lows go in a counterclockwise. Let's put him here. Let's put the low here. And they go in a counterclockwise direction like that. Well, if it's going like this, guess what sometimes a low does? It picks up moisture. It picks up a large amount of moisture from the Gulf of Mexico, and it starts throwing it up our way. And we can actually get a lot of rain that way. Yes?
Wait, in your drawing that you did just now of the high pressure, not the one of the United States, but the one below,
Yeah.
if it's moving in a clockwise direction, wouldn't it be coming from like the southeast?
Oh, uh-oh. I made a mistake. Hey, that's good. I made a mistake. I apologize. This is a high, isn't it? And high is still going clockwise. I made a mistake. All right, bad mistake. Sorry. Hey, thanks for catching that. That was great. This was a high. No, good job. No, good job. You're right. I went counterclockwise. So it's going clockwise. So the winds will go from northwest to what? What's this guy? Southeast, wasn't it? That's a good catch. I made a mistake. Good. Thank you. All right, everybody got that? Now let's go to a low. What are the characteristics of a low? Well, first of all, it's kind of like a valley of air. And wow, now there's going to be less air sitting on top of my barometer. If you have less air on that right there, what's going to happen to the column of mercury? Remember, it's the air pushing on that mercury that keeps it from falling. What if there's less weight of air sitting here? It will allow the mercury to fall. And if you become a meteorologist, the corniest joke you can tell is, hey, the mercury's falling. Why don't you catch it? Okay, so that's a stupid joke. Anyway, so if they say the mercury's falling or the barometer's falling, go catch it. Okay. But what they mean is it's a low pressure system coming there. And so that's a valley of air. The barometer falls. And air is going to be trying to be filling in. They're going to try to fill in that trough of air. And in the northern hemisphere, the air, in this case, instead of falling clockwise, it's going to be rising counterclockwise. Now, if there's any kind of moisture in the air and it's rising like this, then it's going to form clouds. So lows are always associated with storms because this is where your storms are. Now, so lows go counterclockwise in the northern hemisphere. I had somebody last period, they had a phone out, and I thought that was okay. And they actually looked up 30 inches of mercury is about normal atmospheric pressure, 30. And he said, what's the highest? And I didn't know. I didn't know the highest ever recorded. And what's the lowest ever recorded? I said, I bet the low would be some kind of a hurricane or something like that. Because your low pressure things are tornadoes and hurricanes. Okay? And he looked it up, and here's some numbers here. I guess in the Gobi Desert in 2001, and I don't know the exact reason why, but somewhere in the Gobi Desert they had this high pressure system. It was a mountain of air, and it recorded the highest ever in history, 32.06 inches of mercury. And then he looked up another one. It was not only a typhoon, it was a super typhoon. And I guess super typhoons, by the way, that's what they call hurricanes in the Pacific Ocean. I call them typhoons. I don't know why I just call them hurricanes. But anyway, I thought when you get down to 29, you're going to have a bad storm here. So imagine 27, that's like tornado. And this is 25. I can't even imagine being in that storm. The winds would be huge. The pressure difference would be so huge. High winds. And 25.69. I guess that's the absolute record. All right, questions on meteorology? Yes?
So when it's like in the summertime and it's like storms a lot, but it is kind of fast after the good weather?
Well, I would say if it was a storm, most of the storms are from low pressure systems. Here's what sometimes you can do. Sometimes you have this thing called a front. I'm not here to teach meteorology, but what if you had some warm, moist air just kind of sitting here? Just kind of sitting there. It's really humid. And then somehow a bunch of cold air called a front was just moving its way from Canada down here. And cold air is more dense than warm air. So here's what happened. This wedge of cold air would come here and take my warm air and say, whoop, whoop, whoop. And that's another way you could actually have clouds form there. You could have a cold front moving warm air up in the air, and that would cause clouds too. Is that what your question was?
Yeah.
So yeah, if it's not a low pressure system, you could actually have cloud forming another way with a thing called fronts. And again, I'm not here to teach a lot about meteorology. Well, I want to show you, I want to do a couple mathematical things. I thought we'd have time for a few demonstrations. Tomorrow, I expect to do over 15 demonstrations. I'm hoping we're going to be here. And I think you'll like them. Some are very memorable. And even if I don't get finished, I'll try to do some the next day. I want to show you real quickly. Did anybody happen to read this story right here? Or did you read this story, either one of those? I gave you the packet because I got it from another book, and I think it actually adds a little bit more history than your book does. And does anybody know who is this trying to show? Who are they talking about here? Who are these people? One of them did so much work on pressure, they actually named the SI unit of pressure for him, Pascal. Now, Pascal, he was interested in this idea of pressure and air pressure, and it said here he was not in great health at the time. And so he said his brother-in-law, he gave his brother-in-law a balloon, and it was partially filled with air, partially. He says, well, I'm not going up that mountain, you go up that mountain. And so he climbs up the mountain, and he said, you tell me everything you saw and measure it and whatever. And what happened to the balloon? It actually got bigger and bigger. And that's actually the first person to actually know that pressure got less, air pressure got smaller as you went up and up and up. And so that's one of the things he did. Now, another experiment was done, and this one I'm going to show you, I think I can show you on the internet. Let me see here. Minimize that. Let's go to here. Here we go. This is, and I actually gave somebody extra credit. I didn't want to pay $80 for a really big one of these pictures, but I did pay about $10 for that one. And they found it on the internet, and they it was laminated and everything. Anyway, that's a print of a very famous event that happened in air pressure, and I'm going to read the story to you a little bit. Can you see this picture pretty well? All right, that's kind of like this one. And what you see is these are called the Magdeburg hemispheres, and in reality they're about this big. Okay, if you put them together, they make a ball about this big, not huge, and they're made out of, I think, copper, and they used the gasket was leather soaked in oil, so when you put them together, they could kind of make a seal. They actually knew how to make a vacuum pump in the 1600s, believe it or not, and they took all the air out of this hemisphere, this hollow ball, and they sealed it. And then what did they do? Look down here. See these horses? A team of 8 horses that way, a team of 8 horses that way, and whoosh, whoosh, like that. And he had a bunch of people from the town who were watching this, and there's the Magdeburg hemispheres right there. And they could not pull those two half hemispheres apart from each other. Then he stopped the horses, opened up the valve, the air rushed in, the hemispheres fell apart. It was easy to take them apart as long as you didn't have a big pressure difference. You get it? And they said, this is powerful. Air pressure difference is powerful. So I'll show you real quickly. Let me see if I can find, there you go. All right, Magdeburg hemispheres are a pair of large copper hemispheres with mating rims. They're used to demonstrate the power of atmospheric pressure. When the rims were sealed with grease and the air was pumped out, the sphere contained a vacuum, could not be pulled apart by teams of horses. And by the way, it wasn't sucking. There's nothing that sucks. It was just air pressure difference, and it was pushing on the outside there. The Magdeburg hemispheres were invented by a German scientist who was the mayor of Magdeburg, and that's why they're called the Magdeburg hemispheres. Okay, and I don't know how to say his name, so I always say Otto von Guericke, because I don't know how to really say it. And anyway, he said here he wanted to demonstrate this, and okay, so then he did that experiment, and here they are. Here is the real one. This is kept in let's see, what town are they kept in? Maybe it's in, there it is, in Munich. If you go to Munich and you visit that museum, you'll be able to see Otto von Guericke's thing. Anyway, I want to show that to you. I have a small mini version of that, and if you're here tomorrow, I will, it's not like this one. I didn't pay very much money for it, but you'll have difficulty pulling the two hemispheres apart. Because I'm gonna hook up the vacuum pump, we're gonna take the air out of it, and we're gonna see if we can pull it apart. So we'll be doing that. Okay, now what I'm gonna do is I'm gonna get just a little bit mathematical with you, and I wanna finish up some of the scientists, and then I'd like to really do almost the rest of the time do demonstrations. So I'm almost done teaching, okay? Yes? Yeah, good. Okay, so let's take a look over here. This guy here was known as kind of like they say the father of modern science. I don't know. What he did is when he came around, the Renaissance, they wanted everything to be new, and they wanted things to, art was new, and literature was new, and science was new, and he said, I think if we're going to say science is going to go anywhere, it's going to be based on not what you think, but it's based on experiments. And so that's one of the things Boyle did. His name was Robert Boyle. And so that did help. That did help because at that point, everybody had to start doing experiments to prove or disprove something was true or not true. And what he did was, Boyle's law is the most famous pressure volume law ever. And let me tell you what he did. This is not like a barometer. So what he did was he poured some mercury. See this tube? The tube's almost the same except it's bent. See that? When he poured mercury into this thing here, he left the air in here. You get that? And so there's air in here, and of course there's air here because it's open, isn't it? Now, the air pressure here was the same as here, and that's why these two levels are the same. So this is the way he started out his experiment. Another thing that Boyle's named for is when you do experiments, he wanted to be quantitative experiments. Do you remember that word? What did he mean by quantitative? Based on what? Measured numbers, right? And so this is the first of the really carefully measured experiments that were done. And so what he did was he measured here and say that's my starting point with this much weight of air, with this weight of air here. There it is right there. Well, then he started putting more mercury into the tube. And so as they put more mercury in the tube, what happened over here on this side? The pressure on this side went up, didn't it? So he increased the pressure on this side. What happened to the volume of air over here? It shrunk, didn't it? And so as the pressure went up, the volume went down. And I'm going to show you some actual numbers that he did, and then you'll see what I'm talking about here. You guys are very mathematical, so I think you can appreciate this. On the packet, I gave you this right here, and I'm actually going to have you do this experiment later. After Density Detectives, though, I'm going to get LabQuest out, and I will let you do Boyle's Law, and you'll have a barometer, you'll have a pressure gauge, pressure meter, and you'll get some of the best data I've ever seen, ever. Anyway, so you'll get a graph that looks something like this. And if you look at it, as pressure increased, volume decreased. Is that right? Everybody got that? You know how you remember that? Let's take a little balloon. Think about a little tiny balloon and increase the pressure on that balloon. What happens to the volume? Pressure increase, what happens to the volume of the balloon? It decreases, doesn't it? So are they inversely proportional? Let's try it. We don't know. Let's try it. So here's what the book says. If they said Boyle's Law, the book says this. Hey, there's Boyle's Law. There you go. What do you think about that? PV equals K. All right. Whatever that means. What does that mean? When I was your age, I didn't know what that meant. I like math. Hey, give me some numbers. I'll plug them in. Yes?
As pressure goes up, volume goes down.
And they're on the same side of the equal sign, aren't they? And if this is held constant, it is. What if the pressure got 5 times bigger? What happened to the volume of the balloon? 5 times smaller. What's another way of saying 5 times smaller? The volume would go to 1/5 of what it used to be. You get that? Now, here's something I didn't understand. I really didn't. I loved math, but I never knew how to apply certain things in math. I was good at plug and chug and mechanics of math, but I didn't understand how to apply it, okay? Another book will say this. P1V1 equals P2V2. What? Equals P3V3. What's that? What are you trying to say? And here's what they're saying. If we had had a direct proportionality, remember this? Remember mass and volume? If we had a direct proportionality, what's constant? What's constant here? Is volume constant? No. Is mass constant? No. Is anything constant? What? The slope. And what's the slope of this graph? Y over x, isn't it? Isn't that right? If you had a direct proportionality, the constant is the ratio. A ratio of the variables is constant. But look at an inverse proportionality. Say it, say the word. In an inverse proportionality, the blank is constant. Not the ratio, but the what? Starts with a P. R, not pressure. O. D. Math people. What is it? Who somebody said it? Product. The product is constant. So what that means is, look over here. Here's my data table. Oh, that's getting bigger and bigger. Well, that's getting smaller and smaller. I think it might be an inverse proportionality. Let's test it. Watch. What is P, this P, times this V? It's that number. What's this P times that V? Oh! And there's a little bit of error. You take anywhere on this graph, my P times my V equals that P times that V. Everywhere on that graph, the P times V gives you the same number. And that's how you know it's an inverse proportionality. And so some books say, that's Boyle's law. Any P times any V on that graph is a constant. And guess what? Take any point, P1, V1, and all of them equal K, don't they? So that's the first math I wanted to show you. And the second math I want to show you, and that's Boyle's law, right? Everybody got Boyle's law? Pretty easy. I'll show you one more. Uh-oh. I gotta find it. E. I knew you're here. I knew you're here. Right on the back. Okay, see this one? Another guy, Charles Law. Now, Charles Law, I used to watch a TV show. It wasn't that good. It was called Charles in Charge, and it was on TV. And that was my memory trick, because I know that Charles Law always has to do with temperature, not pressure and volume, but temperature and volume. And so what they did is, they took some numbers here. Watch, 0, 50, 25, 55, hey, let's get a little colder, okay? Hey, that's as cold as we can get. Oh man, I wonder what would have happened if we could have gotten colder. I don't know. Let's extrapolate the data, and whoa, that's something weird. You're telling me the volume gets smaller and smaller and smaller and smaller until it's 0? How can the volume of a gas be 0? I don't know, but that's a weird place. I think that's the coldest you could ever get. What? What are we going to call it? And that's how they made the first discovery of what they think was absolute 0. Now, this is not a direct proportionality. Give me 10 seconds. It's not a direct proportionality, is it? Because they can go through 0, 0. But guess what? Don't use Celsius, use Kelvin. And now what do you get? Look what you get there. If you use a Kelvin temperature, if you start at 2 Kelvin and you go to 10 Kelvin, what's going to happen to the volume of that gas? The temperature got 5 times higher, didn't it? The volume of that gas will get 5 times higher. Everybody got it? Okay, tomorrow I'm going to do a lot of demonstrations. I'm hoping you're going to be here. Keep reading the book. Everybody reading the book? I'm going to spend a lot of time with Bernoulli. Find out who Bernoulli was. I'll have the vacuum pump out tomorrow. I'll have a vacuum cleaner, a vacuum pump. I'll have Magdeburg hemispheres. I'll try to get as much as I can, squeeze as much as I can in 1 hour. I hope we're going to be here. You're welcome. Thanks. Hey, thank you, everybody, for all the questions.